Early June 1944. A heavy American tank rumbles out the gaping bow doors of a landing ship, expecting its tracks to bite into solid sand. Instead, it hits a floating steel platform surrounded by dark seawater. Transport ships are forced to anchor miles offshore, blocked by a massive tidal flat of soft mud and ruined infrastructure, with absolutely no conventional port in sight. Drive a 30-ton war machine directly into that surf, and it instantly becomes a submerged steel coffin. How does an invading army offload thousands of heavy vehicles onto a hostile coast where there is no pier, and the massive tidal shift turns the beach into an inescapable trap? The answer wasn't a pre-existing harbor. It was an unprecedented, highly adaptable, modular system engineered by the U.S. Navy Seabees. To sustain the invasion, the American contingent would quickly require a staggering flow of reinforcements, scaling to thousands of tons of supplies every single day. But the uncompromising geographical reality of the Normandy coast stood in the way. Deep draft transport ships cannot approach the sand. Smaller landing craft risk getting hopelessly stranded by the rapidly retreating tide. And attempting to unload heavy trucks and armor, one by one, into the soft, sinking mud creates a fatal bottleneck. These massive physical barriers, deep water, violent tidal shifts, and unstable terrain meant the mechanized Allied forces were effectively cut off from the fuel and artillery they needed to survive the beachhead. This is the story of how the Seabees bridged that impossible gap. They didn't do it by attempting to build a single, fantastical highway across the ocean. Instead, they engineered a brilliant combination of motorized Rhino ferries and sunken pontoon causeways, turning ordinary steel boxes into a dynamic lifeline. But before a single tank could safely roll onto the French shore, the engineers had to confront a fundamental logistical nightmare. If the transport ships cannot touch the land and the heavy vehicles cannot touch the water, how do you physically transform the churning sea and a treacherous beach into a solid route for a 30-ton machine? To understand the sheer scale of the crisis facing the Allied invasion, you have to look down at the dirt and the water. The Normandy coastline is not a sheer cliff drop into the abyss, nor is it a deep-water harbor. It is a treacherous, highly deceptive slope of sand and mud. For a military planner in 1944, this geography was a nightmare. The backbone of the American amphibious heavy lift capability was the LST, the landing ship tank. These were massive, ocean-going vessels nearly 330 feet long, capable of carrying hundreds of tons of armor and transport vehicles directly in their bellies. But an LST fully loaded with Sherman tanks, heavy artillery, and supply trucks sits deep in the water. It requires a specific depth to float and a relatively steep beach gradient to get its bow doors anywhere close to dry land. The French beaches at Omaha and Utah did not offer that gradient. Instead, they stretched out in a long, shallow shelf. If an LST captain tried to drive his ship directly onto the beach, the vessel's hull would grind into the sandbank hundreds of yards offshore. The ramp would drop not onto solid ground, but into deep, swirling seawater. Any tank or truck rolling off that ramp would immediately plunge into the channel and sink like a stone. Because of this brutal physical constraint, the massive LSTs had to drop anchor far out in the deeper waters. The conventional naval solution was to transfer the men and machines from the large ships into smaller, shallow draft landing craft. But here, the English Channel presented a second, equally ruthless, physical barrier: the tide. The tidal range along the Normandy coast is extreme, shifting by roughly 20 feet. When the tide goes out, it retreats with alarming speed, exposing hundreds of yards of saturated tidal flats. If a small landing craft successfully navigated the surf and dropped its cargo onto the beach at high tide, it had a rapidly closing window to back out. Miss that window by just a few minutes, and the boat was grounded. It would sit hopelessly marooned on the wet sand for hours until the next high tide rolled in to lift it free. A stranded landing craft is a useless landing craft. It cannot return to the offshore fleet to pick up more troops or supplies. The cycle of reinforcement is instantly broken. You cannot sustain a rapid invasion if half your delivery vehicles are sitting paralyzed on the shoreline for most of the day. Even when a vehicle managed to reach the shoreline without the boat getting stranded, it faced the immediate peril of the tidal flat itself. This was not the firm, packed sand of a resort beach. This was a treacherous mix of soft sand, shifting shingle, and deep mud, constantly saturated by the retreating sea. A 30-ton tank, or a 2.5-ton cargo truck, heavily loaded with ammunition, applies immense ground pressure. When these heavy machines rolled off a landing craft and hit that wet, unstable surface, they quickly bogged down. Tires spun helplessly, digging deeper trenches. Tank tracks churned the soft mud into an impassable soup. A single trapped vehicle in the middle of a designated landing lane was a tactical disaster. It blocked the path for everything coming in behind it. Suddenly, you have a massive, stationary traffic jam of highly explosive cargo sitting completely exposed on an open beach. Under the brutal reality of an opposed landing, with enemy mortar and artillery fire zeroed in on the shoreline, a stationary truck is a doomed truck. The entire unloading process risked grinding to a catastrophic halt, paralyzed by nothing more than the physical composition of wet dirt. This geographical trap collided violently with a relentless mathematical reality. An invading mechanized army is a living, breathing beast with an insatiable appetite. You cannot just land soldiers on a beach and expect them to fight indefinitely. They require a staggering, continuous pipeline of material just to hold the ground they have taken, let alone push inland. The logistical planners had run the numbers, and the requirements were astronomical. By D+4, just 4 days after the initial landings, the American contingent would require a daily injection of approximately 6,000 tons of general supplies. 6,000 tons every single day. And that number was not static. It was designed to skyrocket as more divisions poured into the bridgehead. By D+10, the requirement would scale up to 9,000 tons daily. By D+16, the American forces would need over 12,000 tons of ammunition, fuel, rations, medical equipment, and spare parts delivered across that beach every 24 hours just to maintain their combat effectiveness. Think about the sheer volume of 12,000 tons. Now look back at the beach. You have heavy transport ships trapped in deep water miles offshore. You have smaller landing craft that get stranded by the violent shifting tides. And you have a treacherous, muddy coastline that swallows heavy trucks the moment they try to drive across the exposed flats. Unloading an entire mechanized army and its required daily tonnage, one vehicle at a time, ferrying them slowly through the surf, risking stranding and dragging them through the mud, was a mathematical impossibility. The rate of delivery through conventional means could never match the rapidly accelerating rate of consumption on the front line. If the flow of supplies choked at the water's edge, the combat units pushing into the hedgerows would quickly run out of bullets. Their tanks would run dry of fuel, and the entire invasion would collapse. The front line would literally starve for resources, while millions of tons of desperately needed supplies sat perfectly safe but completely inaccessible in the cargo holds of ships anchored just over the horizon. The survival of the American invasion force depended entirely on breaking this physical bottleneck. The traditional rules of amphibious warfare had completely broken down under the weight of the massive supply demands and the harshness of the French coast. A completely new approach was required to span that deadly divide. If the massive ships could not touch the sand and the heavy trucks could not touch the mud, how could engineers possibly transform deep water and soft sand into a heavy-duty transit route for tanks? The solution did not come in the form of a massive new class of transport ship. It came in the form of a standardized, seemingly unremarkable steel box, the Navy pontoon. By linking hundreds of these watertight steel cubes together, the U.S. Navy Seabees engineered two entirely distinct mechanical beasts designed to permanently bridge the gap between the deep water and the dry land. The first was the Rhino ferry. This was not a delicate, improvised raft. It was a massive, motorized barge, measuring 176 feet long and 42 feet wide, constructed entirely from interlocking pontoon sections. Equipped with its own heavy-duty outboard engines, the Rhino was designed to act as a dynamic, autonomous shuttle. It could pull directly alongside a deep-draft landing ship anchored miles out in the channel, take on 30 to 40 heavy vehicles straight from the ship's belly, and then power its way independently through the surf zone. But a ferry still needs a secure place to unload. Dropping 30 tanks directly into the shallow surf still risked the fatal mud trap of the tidal flats. That is where the Seabees introduced their second crucial concept, the sunken pontoon causeway. It is vital not to confuse this American design with the British whale bridges. The whale was a flexible, floating roadway. The American pontoon causeway was engineered as a rigid, heavy steel path extending out across the tidal zone. When the tide was high, Rhino ferries and small craft could dock against it like a traditional pier. But when the violent Normandy tide retreated, this massive steel structure did not float away. It settled directly onto the wet sand. It created a solid, unyielding surface that allowed heavy trucks and armor to roll safely from the water's edge straight onto the firm ground of the beach, completely bypassing the treacherous mud. Building this modular lifeline required a massive industrial mobilization. Beginning in late 1943, secret assembly yards sprang to life along the English coast at Falmouth, Plymouth, and Dartmouth. The pressure was immense. To support the sheer scale of the invasion, the Seabees had to fabricate and prepare exactly 36 of these enormous Rhino ferries for the Omaha and Utah sectors, alongside thousands of feet of causeway equipment. To execute this complex mechanical choreography, the Navy divided the labor among highly specialized units. The 111th Naval Construction Battalion was assigned to pilot the Rhino ferries into the meat grinder of Omaha Beach. The 81st took the helm for the ferries bound for Utah. A dedicated unit, the 1006th Construction Battalion Detachment, was tasked specifically with wrestling the heavy, sunken pontoon causeways into place on both American beaches. Meanwhile, maintaining strict Allied coordination, the 108th Seabees trained to assemble the separate British-designed whale bridge components that would eventually integrate into the larger artificial harbor at Omaha. The logistical survival of the American military now relied entirely on this intricate web of Allied cooperation and untested modular architecture. The Seabees were staking the momentum of the invasion on 36 experimental ferries and thousands of bolted steel cubes. On paper, the system was a logistical masterpiece. The mathematical models worked perfectly in the quiet assembly yards of Cornwall and Devon, but a critical question remained hanging over the entire operation. What happens when these flawlessly engineered blueprints collide with the chaotic, violent, and unpredictable reality of the French coast on the morning of D-Day? The reality of the English Channel on the night of June 5th immediately stripped away the illusion of a flawless mathematical model. As the invasion fleet pushed southward in the darkness, the massive landing ship tanks did not just carry cargo in their bellies. They dragged the Seabees' untested infrastructure directly behind them. The 36 Rhino ferries, each a sprawling steel footprint of 176 feet, were tethered to the sterns of the LSTs by thick towing hawsers. This was not a smooth transit. The channel was rough, churning with a heavy chop that constantly threatened to snap the cables. The men of the 111th and 81st Naval Construction Battalions rode these unwieldy steel rafts through the night, exposed to the freezing spray and the relentless pitch of the ocean, fighting to keep the heavy outboard engines functional and the pontoon connections secure before they even reached the combat zone. But simply surviving the crossing was only the prologue. The true mechanical crucible began miles off the coast of France in the early hours of June 6th. To transfer 30 tanks from the belly of a pitching ship onto a floating platform, the Seabees had to execute a highly dangerous naval maneuver known as the marriage. The procedure required absolute precision in an environment defined by chaos. The Rhino ferry had to maneuver its stern directly against the massive steel bow doors of the LST. The ship would then lower its heavy ramp, bringing the edge of the ramp to rest precisely on the deck of the ferry. In calm waters, it was a delicate operation. In the churning swells off Normandy, it was a terrifying collision of raw physics. The LST and the Rhino ferry possessed entirely different centers of gravity and buoyancy. As the ocean heaved, the massive ship and the flat steel raft moved violently out of phase. The ship would rise on a swell, while the ferry plummeted into a trough. The steel ramp, weighing tons, ground and smashed against the pontoon deck. Men were caught in the middle of this shifting geometry, desperately trying to secure heavy mooring lines and chain binders between the two pitching vessels while avoiding being crushed by the grinding steel. The original engineering blueprints dictated that this marriage procedure was safe only in swells of 3 feet or less. On the morning of D-Day, particularly off the coast of Omaha Beach, the waves were cresting at 6 feet. The ocean was delivering exactly double the maximum kinetic energy the system was ever designed to absorb. The mooring lines snapped under the sheer tension like rifle shots. The heavy steel pins connecting the pontoon blocks groaned and buckled under the violent torque. And even when a Seabee crew successfully managed to chain the ferry to a ship, the friction of war threw another massive variable into the equation. The initial assault waves had not cleared the beach. The intricate network of German underwater obstacles, the steel hedgehogs, the wooden ramps rigged with teller mines, the jagged metal gates, remained largely intact, hidden just below the surface of the rising tide. The Rhino ferries, now loaded with hundreds of tons of desperately needed Sherman tanks and half-tracks, were entirely blocked from the shore. They became massive, highly explosive targets, drifting in a lethal holding pattern just outside the surf zone, pounded by the 6-foot waves, while artillery shells threw geysers of seawater into the air around them. The pristine timeline drawn up in London was already disintegrating. From the elevated bluffs overlooking the sand, the German defenders watched this chaotic armada with a grim, calculating confidence. The German tactical doctrine for the defense of Western Europe was anchored in a fundamental logistical assumption. The Allies absolutely required a deep-water port to sustain an invasion. The German High Command knew the mathematics of mechanized warfare just as well as the Americans. They understood that an infantry assault could cross a beach, but a modern army required an uninterrupted flow of heavy armor, artillery, and motorized transport. By heavily fortifying existing ports like Cherbourg and Le Havre, and leaving the open beaches defended by obstacles and interlocking fields of machine gun fire, the German command believed they had effectively paralyzed the Allied heavy lift capability. As the German artillery officers and coastal defense commanders peered through their optics on the morning of June 6th, they expected to see the Americans struggling to push a handful of vulnerable vehicles through the mud, slowly bleeding their momentum against the natural defenses of the tidal flat. But as the morning progressed, the view through the German binoculars began to shift. The chaotic mass of ships offshore was not just offloading infantry into small, easily destroyed wooden boats. Massive, low-slung steel rafts were separating from the larger ships. They were heavily laden with armored vehicles, sitting precariously low in the water, but they were moving under their own power. The creeping anxiety among the German observation posts was not born from the sight of overwhelming numbers, but from the sudden, chilling realization of what these rafts represented. The Americans were not attempting to capture a port to unload their heavy armor. They had dragged the port across the ocean with them. The rigid defensive doctrine that relied on the absolute denial of port facilities was suddenly unraveling before their eyes. The enemy was bringing their own infrastructure directly to the sand. The psychological impact of this realization was matched only by the sheer physical exertion required to make it a reality. Aboard the Rhino ferries, the men of the 111th and 81st Seabees were operating entirely outside the boundaries of their training manuals. The heavy outboard propulsion units, designed for maneuverability, struggled against the fierce coastal currents and the drag of the heavily loaded pontoons. Water washed continuously over the flat decks, drenching the vehicle crews and the Seabees alike. Navigation was an exercise in localized terror. The ferry commanders had to thread a massive, unwieldy rectangle of steel through narrow gaps in the mined obstacles, constantly reading the shifting surf to avoid grounding the pontoon on a submerged sandbar or striking a live explosive. There was no steering wheel. Direction was controlled by independently throttling the massive outboard engines on the stern, requiring precise, immediate communication over the deafening roar of the surf, the engines, and the incoming artillery fire. Every successful transit from the offshore LST to the beach was a minor miracle of improvised seamanship. When a Rhino finally touched the sand, the heavy vehicles did not hesitate. Tanks roared to life, their tracks slipping briefly on the wet steel deck before gripping the French soil, instantly multiplying the combat power of the infantry pinned down on the beachhead. But dropping vehicles into the surf zone was still only a partial solution. The mud remained. The tidal shift remained. The true heavy lift capacity required the rigid steel pathways. The burden of bridging the mud fell directly on the 1006 Construction Battalion Detachment. Their mission was to assemble and anchor the sunken pontoon causeways, the heavy steel arteries that would connect the water to the dry beach. At Utah Beach, the geographical conditions, while challenging, were marginally more forgiving than the slaughterhouse of Omaha. But there was nothing easy about wrestling hundreds of feet of bolted steel in a combat zone. The causeway sections were towed across the channel in massive pre-assembled strings. Once off the coast of Utah, the Seabees had to maneuver these heavy strings through the surf, align them perfectly with the designated landing zones, and physically pin them together to form a continuous, rigid pier. This was brutal, freezing, and exhaustingly physical labor. The men of the 1006th worked chest deep in the cold channel water, fighting the relentless push and pull of the tide. They used heavy sledgehammers to drive the massive steel linking pins into the pontoon joints, their hands slipping on the wet metal, while German mortar fire periodically bracketed the shoreline. The geometry of the causeway was critical. If it was not perfectly aligned, or if the anchoring system failed, the entire structure would twist and buckle under the immense weight of the incoming vehicles. But the Seabees at Utah pushed through the friction of the environment, working continuously through the first critical days of the invasion, adjusting their techniques on the fly as they learned how the local tide affected the buoyancy of the pontoons. They achieved a major logistical breakthrough. By June 8th, just 2 days after the initial assault, the 1006th Seabees established the first fully working sunken pontoon causeway at Utah Beach. The sight of the first heavy trucks rolling smoothly off a landing craft, driving securely down a steel road directly over the mud, and reaching the dry beach without bogging down, proved that the fundamental engineering concept was sound. The bottleneck was breaking. However, the success at Utah did not immediately translate to the much harsher environment of Omaha Beach. Here, the rigid engineering blueprints collided violently with a highly complex and unforgiving terrain. The initial design for the Omaha causeways called for a standard 2-pontoon width, projecting straight out into the surf. But when the Seabees attempted to lay the steel, the reality of the Omaha tidal shelf aggressively rejected the plan. The beach gradient was uneven, scarred by deep runnels and shifting sandbars. The violent cross-currents continuously battered the long, thin string of pontoons, threatening to shear the entire structure apart. Furthermore, the sheer volume of traffic demanding access to the Omaha beachhead was overwhelming the narrow design. A 2-pontoon width was too restrictive for the massive outward flow of vehicles, creating a dangerous traffic jam precisely where the vehicles were most vulnerable to artillery. The American engineers realized instantly that adhering to the original plan would be fatal to the logistical timeline. They had to redesign the infrastructure in the middle of a war zone. The Seabees at Omaha made a radical, rapid adaptation. They halted the initial installation and began ripping the structure apart to rebuild it stronger. They widened the causeway from 2 pontoons to 4, drastically increasing its structural integrity against the heavy surf and providing a much broader avenue for the massive supply trucks. To prevent the structure from buckling over the uneven sandbars, they shortened the overall length to approximately 1,450 feet. But the most critical adaptation was functional. Instead of treating the causeway merely as a road leading to the end of a pier, they engineered it to act as a massive, multi-sided docking platform. The Seabees reinforced the sides of the widened causeway so that Rhino ferries and smaller landing craft could pull alongside and offload onto the flanks of the structure, rather than waiting in line to use the tip. This required hundreds of men working in the freezing surf, unbolting and rebolting tons of steel under the constant threat of enemy fire and the relentless pressure of the tide. The men slept in the sand, ate cold rations, and returned to the water, driven by the absolute necessity of opening the supply valve. The friction of the environment fought them for every single inch of progress. But the modular nature of the pontoon system, the very fact that it was not a single, rigid structure, but a collection of adaptable blocks, allowed the engineers to dynamically respond to the terrain. Slowly, painfully, the new, wider and shorter causeway took shape across the Omaha tidal flat. A second causeway was initiated on June 13th to handle the escalating volume. By June 16th, the massive redesigned steel artery at Omaha was fully operational, transforming a deadly, muddy trap into a heavy-duty industrial thoroughfare. The flow of artillery shells, medical supplies, and aviation fuel accelerated dramatically, pouring directly into the veins of the 1st United States Army. The Seabees had proven that they could physically overpower the English Channel and the French mud through sheer adaptability and raw mechanical force. They had successfully built a road where no road could exist. But as the invasion pushed deeper into Normandy, the demands of the mechanized army were shifting, and the volume of cargo was rapidly exceeding the original calculations. The static steel infrastructure was bolted to the sand, heavily reliant on a delicate balance of favorable tides and manageable surf. The defining question was no longer whether the American engineers could build a pontoon bridge to the beach. The question was whether a rigid, highly exposed string of steel boxes could possibly survive when the fundamental nature of the environment inevitably turned against them. The true genius of the Seabee engineering was not just that it successfully bridged the water, it was that the system refused to remain static. The defining characteristic of the artificial harbor was its extreme adaptability in the face of a rapidly evolving war. By roughly D+7, the fundamental dynamics of the invasion beaches began to shift. The massive LSTs, originally deemed too deep and too heavy to risk approaching the sand, were suddenly changing the rules. American naval crews had learned how to aggressively ride the incoming tide, deliberately beaching their 300-foot ships directly onto the tidal flats. When the water rushed out, the ships simply rested flat on the muddy bottom, dropping their massive bow ramps to offload directly onto the sand before floating free again on the next high tide. On paper, this sudden tactical evolution should have rendered the entire Rhino ferry system obsolete overnight. If the massive ships could suddenly touch the beach, the dangerous and complicated mid-ocean marriage of steel rafts seemed completely unnecessary. But the motorized steel boxes did not become useless relics of the first week. Instead, the Rhino crews executed a brilliant operational pivot. While the LSTs took over the direct delivery of heavy armor, a massive fleet of Liberty ships and deep draft freighters was arriving off the coast, packed with the crushing volume of general cargo, ammunition, and rations required to feed the advancing army. These deep-hulled merchant vessels could never approach the beach without tearing their bottoms out on the sandbars. The Seabees immediately redirected their fleet of Rhino ferries away from the LSTs and straight toward the freighters. The wide, flat pontoon decks proved perfectly suited for catching heavy cargo nets swung down from the Liberty ship's towering derricks. The system adapted flawlessly, transforming instantly from an emergency vehicle shuttle into the primary heavy cargo lifeline of the American sector. The sheer volume of material pushed across these improvised steel arteries was staggering. During the first 10 days of the invasion, official naval logs credited this highly adaptable system with landing approximately 5,286 vital vehicles onto the sands of Utah Beach. At Omaha, the numbers were even more overwhelming, with roughly 16,000 vehicles successfully brought ashore across the pontoons and ferries. It was an unmitigated logistical victory. The Seabees and their modular steel boxes were feeding a mechanized army at a rate that completely defied the harsh geography of the French coast. The American supply machine was finally humming with relentless industrial precision. The bottleneck was broken, the offshore fleet was rapidly unloading, and the beaches were clear. But just as the engineers achieved total mechanical dominance over the shoreline, the atmospheric pressure began to drop. The barometer plummeted, the wind shifted violently, and the sky over the English Channel turned pitch black. On June 19th, the English Channel unleashed a fury that eclipsed any artillery barrage the German army could muster. It was the worst summer gale to hit the Normandy coast in 40 years, and it did not pass quickly. For 3 relentless days, the storm hammered the exposed invasion beaches with blinding rain and gale-force winds, transforming the sea from a conquered logistical highway back into a violent, chaotic barrier. The Seabees and their modular steel system were suddenly subjected to a trial far beyond their original engineering limits. The true danger of the storm was not merely the sheer kinetic force of the water crashing against the pontoons. It was the chain reaction of chaos occurring out in the deep anchorage. The offshore water was packed with hundreds of transport ships, barges, and landing craft. As the relentless waves heaved the massive hulls up and down, heavy mooring lines snapped under the extreme tension. Anchors dragged helplessly across the ocean floor. Dozens of vessels were torn violently loose from their moorings, cast adrift into the raging surf. Pushed by the screaming wind, these uncrewed, drifting ships transformed into massive, uncontrollable steel battering rams. They were hurled directly toward the vulnerable artificial infrastructure the Americans had spent weeks bleeding to build. At Omaha Beach, the destruction was catastrophic. The violent surf caught the massive Rhino ferries, the heavily loaded 176-foot motorized barges that had been moving thousands of vehicles just hours before. The ocean lifted these enormous steel rafts and violently threw them onto the shingle. Pounding waves continuously slammed the ferries against the beach, buckling their interconnected steel pontoon blocks and shearing their heavy mountings. The critical blow fell on the propulsion systems. The pounding surf battered and crippled the massive outboard engines of approximately 20 Rhino ferries, instantly paralyzing the motorized backbone of the American supply fleet. The once dynamic ferries were reduced to shattered, tangled wrecks of twisted metal scattered across the sand. Down the coast at Utah Beach, the force of nature executed a different kind of mechanical execution. Here, the drifting debris and the driving surf pounded directly downward onto the rigid, sunken pontoon causeways. The massive steel arteries that had perfectly bypassed the treacherous mud were subjected to thousands of tons of continuous, rhythmic pressure from the surging tide. The causeways didn't just break, they were physically driven deep into the beach. The relentless pounding hammered the heavy steel blocks straight down into the useless, saturated sand, completely burying the crucial transit routes under the tidal flat. In a matter of hours, the unstoppable kinetic force of the English Channel achieved what the German High Command had failed to do. It instantly severed the entire American ship-to-shore lifeline. The industrial conveyor belt that was feeding the invasion suddenly ground to a complete halt. Not a single pound of ammunition, not a single gallon of fuel, and not a single replacement tank was crossing the beaches. The frontline forces, locked in brutal combat in the hedgerows, were rapidly burning through their reserves. The surviving Seabees stared out at a coastline choked with the twisted, mangled wreckage of their own engineering triumph. How could they possibly resurrect a shattered logistical network using its own ruined pieces before the American front line simply ran out of bullets? When the skies finally cleared, the Seabees did not wait for shipments from England. The engineers waded back into the freezing surf and began wrestling with the twisted wreckage of their own creation in a desperate race against the front line's dwindling ammunition. This is where the brilliant reality of the pontoon design revealed itself. It was never a monolithic structure. It was a highly adaptable, modular toolkit. If a Rhino ferry was smashed, its surviving steel cubes could be unbolted and reassembled into a causeway, or repurposed as a repair platform. At Utah Beach, the recovery was rapid and brutal. The Seabees physically dug their sunken causeways out of the sand. They raised the heavy steel strings, relocated the entire structure westward to more stable ground, widened the lanes, and shortened the overall length to 1,400 feet. Through sheer mechanical force, Utah's Rhino ferries were resurrected and thrust back into the offshore supply cycle by June 22nd. Omaha Beach presented a far more punishing reality. The devastation there was so absolute that while general beach unloading managed to resume earlier on June 23rd, the mechanized pontoon fleet remained severely crippled. The men were forced to cannibalize their ruined vessels, stripping engine components from dead ferries to breathe life into a handful of survivors. It was a grueling triage, delaying the return of full Rhino operations at Omaha until July 1st. These steel boxes did not single-handedly win the Normandy campaign, nor did they represent the entirety of the artificial harbor project. But without their modular flexibility, the mechanized invasion force would have starved on the shoreline. The American engineering triumph was the ability to take an ordinary steel cube and dynamically forge it into whatever the chaotic reality of the war demanded. Through ferries and causeways, they closed the lethal gap between the deep water and the shallow sand, ensuring the heavy ramp of a transport ship could always find a battered pontoon deck, forging a path over the water for the armor to roll safely onto the French shore. When that massive transport ramp finally dropped into the churning surf, the 30-ton war machine waiting inside did not plunge into the deep channel or sink into the paralyzing coastal mud, but instead bit its tracks hard into a floating pontoon deck and rolled safely onto the firm French shore. The Seabees did not just conquer the heavily defended beaches of Normandy, they actively paved the ocean itself. In doing so, they proved that in the brutal arithmetic of modern mechanized warfare, survival and logistics are no longer just about moving supplies to the edge of the battlefield. It is about building the road exactly as you drive on it.